The story of the most distant traveler in human history does not begin in the cold reaches of the void, but rather in the humid, salt-tinged air of a Florida coastline during the late 1970s. It was a time when our understanding of the outer solar system was filtered through the grainy lenses of ground-based telescopes, a period where the gas giants remained largely as points of light and mathematical abstractions rather than physical worlds. To understand how far Voyager 1 can travel, we must first look back at the precise moment it broke the bonds of our world, propelled by an ambition that bordered on the impossible. This was a machine built by a species that had only recently learned to leave its own atmosphere, yet it was designed to navigate a sea of darkness that stretched across billions of kilometers. The spacecraft was not merely a collection of sensors and aluminium. It was a physical manifestation of a unique window in time, a celestial coincidence that would not occur again for another 176 years. In the mid-1960s, a young aeronautics intern named Gary Flandreau was working at the Jet Propulsion Laboratory, tasked with finding efficient ways to explore the outer reaches of our solar system. He discovered something that seemed almost like a gift from the heavens. The 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, were moving into a rare alignment that would allow a single spacecraft to visit each of them in succession by using the gravity of one planet to slingshot it toward the next. This concept, known as the Grand Tour, was the catalyst for everything that followed. And without this specific planetary geometry, the journey to the edge of the Sun's influence would have taken decades longer and required an amount of fuel that no rocket on Earth could possibly carry. By stealing a tiny fraction of the orbital momentum from these massive worlds, a small probe could be accelerated to speeds that would eventually allow it to escape the Sun's gravitational well entirely. Voyager 1 was launched on September 5, 1977, only weeks after its twin, Voyager 2. While it began its journey later, it was placed on a faster, more direct trajectory that would soon see it overtake its sister craft to become the leading edge of human exploration. The launch itself was a feat of raw chemical power, a Titan Centaur rocket roaring into the sky, it carrying a payload that weighed less than a small car. But inside that modest frame was the most sophisticated technology of the era. To ensure the mission could survive the decades of travel required, the engineers had to account for the total absence of repair opportunities. There was no way to fix a broken lens or a failed thruster once the craft left the vicinity of Earth. Every system was redundant, every line of code was checked 1,000 times, and the power source was not the sun, which would soon fade to a mere bright star, but the slow decay of plutonium dioxide. These radioisotope thermoelectric generators provided a steady, if gradually diminishing, flow of electricity that would serve as the heartbeat of the machine for nearly half a century. The first major milestone of this escape from the solar system was the encounter with Jupiter in early 1979. As Voyager 1 approached the King of Planets, the sheer scale of the challenge became apparent. Jupiter is a world of radiation and crushing gravity, a place that could easily fry the delicate electronics of an unshielded visitor. The navigation teams on Earth had to calculate the trajectory with a precision that seems almost miraculous given the computing power of the time. They needed to pass close enough to the planet to be whipped around by its gravity, yet far enough away to avoid the worst of its lethal radiation belts. As the spacecraft dove toward the giant, it began to send back images that changed our perception of the universe forever. we saw the Great Red Spot not as a static feature, but as a roiling 300-year-old hurricane larger than Earth itself. We discovered that the moon Io was not a dead, cratered rock, but a world of erupting volcanoes, the most geologically active body in the solar system. This encounter with Jupiter was the first true test of the gravity assist maneuver. As Voyager 1 fell toward the planet, it accelerated under the immense pull of Jupiter's mass. If it had simply flown straight past, it would have regained its original speed as it moved away, but by timing the approach so that it was pulled in the direction of Jupiter's own orbital motion, the spacecraft was able to steal a small amount of the planet's energy. In the language of physics, it was an exchange of momentum. Jupiter slowed down by a fraction of a millimeter over billions of years, while Voyager 1 gained thousands of kilometers per hour in velocity. This was the boost that allowed the mission to proceed toward Saturn. The speed gained at Jupiter was essential, for the Sun's gravity is a persistent thief, constantly trying to pull the spacecraft back toward the center of the solar system. To reach the stars, Voyager 1 had to stay ahead of that invisible tether. The arrival at Saturn in November of 1980 marked the most critical junction in the mission's life. Here, a difficult choice had to be made by the mission planners. They could have sent Voyager 1 on toward Uranus and Neptune, continuing the grand tour. But there was a moon orbiting Saturn that held a mystery too compelling to ignore. Titan, a moon larger than the planet Mercury, was shrouded in a thick orange haze. And scientists suspected it might have an atmosphere and perhaps even liquid on its surface. To get a close look at Titan, Voyager 1 had to be diverted from the plane of the planets, the ecliptic. The trajectory required to skim the atmosphere of Titan would inevitably fling the spacecraft upward and away from all the other planets in the solar system. It was a sacrifice of future destinations for the sake of a singular discovery. When the craft completed its flyby of the orange moon, its cameras saw only a featureless cloud deck, but its instruments confirmed a nitrogen-rich atmosphere, a world that seemed to be a frozen version of an early Earth. Once the Titan encounter was over, Voyager 1 was on a path that led only into the dark. It was no longer aimed at any planet, any moon, or any asteroid. It was headed for the edge. The gravity of Saturn had given it one final massive kick, sending it hurtling out of the ecliptic plane at an angle of 35 degrees. From this point forward, the spacecraft was truly a creature of interstellar space, even if it had not yet left the Sun's domain. It was traveling at over 60,000 kilometers per hour, a speed so vast that it covers more than 1.5 million kilometers every single day. Yet, even at this blistering pace, the distances in the outer solar system are so immense that the spacecraft would spend the next 32 years simply trying to reach the exit. During these decades of quiet transit, the spacecraft became a lonely sentinel. It looked back toward the Sun and, in February of 1990, at the request of astronomer Carl Sagan, it turned its camera one last time to capture an image of its home. From a distance of 6 billion kilometers, Earth appeared as a tiny, fragile speck of dust caught in a sunbeam. This pale blue dot image was a haunting reminder of the insignificance of our world in the face of the cosmic scale. But it also highlighted the monumental achievement of the machine that captured it. Voyager 1 was leaving the only home it had ever known, carrying with it the record of a civilization that was still trying to understand its place in the grand design. The cameras were soon turned off to save power, leaving the craft to navigate by the stars and the faint hum of its remaining sensors. The engineering that sustained this flight is perhaps the most impressive part of the initial leap. Because the spacecraft is so far away, radio signals traveling at the speed of light take hours to reach Earth. By the time a controller at the National Aeronautics and Space Administration sees a problem on their monitor, the event has already happened hours in the past. To compensate, Voyager 1 was built with an internal logic that allowed it to protect itself. If it lost its lock on the Sun or the star canopus, which it used for orientation, it would automatically execute a search pattern to find them again. If a memory bank failed, it could reroute data to a backup. These systems, designed with the primitive logic of 1970s transistors, have proven more resilient than almost any machine ever built by human hands. They have survived the intense cold of deep space, where temperatures hover just a few degrees above absolute zero, or by the constant bombardment of cosmic rays that can flip bits in a computer's brain. As Voyager 1 moved beyond the orbit of Pluto, it entered a region of space that no one had ever measured before. For a long time, we didn't know exactly where the solar system ended. The Sun does not have a hard shell. Instead, it creates a massive bubble of charged particles called the heliosphere. This bubble is created by the solar wind, a stream of plasma blowing outward from the Sun at millions of kilometers per hour. For thousands of millions of kilometers, this wind pushes back against the thin gas of the galaxy. Voyager 1 was tasked with finding the boundary where the Sun's wind finally falters and the interstellar medium begins. Throughout the late 1990s and the early 2000s, the spacecraft began to detect a change in its environment. The solar wind began to slow down, piling up like water hitting a wall. The spacecraft was entering the heliosheath, the turbulent outer skin of the Sun's bubble. The journey through the heliosheath was a slow and confusing process for the scientists on the ground. They watched as the instruments on Voyager 1 reported a strange stagnation in the solar wind. At times, the wind seemed to stop moving outward altogether, suggesting that the craft was very close to the edge. Yet, the boundary remained elusive. Year after year, the spacecraft pushed further, its plutonium power source dropping by 4 watts every year, forcing the team to turn off heaters and non-essential instruments. Or the mission had transformed from a planetary flyby into a quest to find the end of our Sun's kingdom. Every bit of data sent back was a new revelation, a measurement of the pressure and magnetism at the very doorstep of the stars. The sheer endurance of the craft is a testament to the people who built it. They used tape recorders with actual moving parts to store data, and they built antennas that could stay pointed at a tiny, distant Earth with the precision of a needle's point. As we contemplate how far Voyager 1 can travel, we must recognize that its first 20 billion kilometers were just the beginning. It was the easy part of the journey, where the Sun's light was still visible and the path was guided by the giants of our own system. But the true journey began the moment the solar wind died away and the craft felt the first touch of the galaxy beyond. It was an escape from the cradle, a final goodbye to the gravitational embrace of the Sun, and the start of a voyage that would eventually outlast the very civilization that conceived it. Voyager 1 was no longer just a probe. It had become an ambassador of a small planet sailing into an ocean of night that has no shore. The final moments of its life within the heliosphere were marked by a sudden and dramatic shift in the particle environment. For years, the spacecraft had been surrounded by particles that originated from our Sun. Then, in the summer of 2012, those particles vanished almost instantly, replaced by a flood of high-energy cosmic rays from deep space. The magnetic field also shifted, aligning itself with the interstellar flow. Voyager 1 had done it. It had become the first human object to cross into the interstellar medium. It was now truly in the space between the stars, a place where the Sun is just one of many, and where the rules of the journey would change forever. The leap into the void was complete, and the long, silent trek into the deep future had officially begun. To cross the threshold of one's own home is an act of profound significance, whether for a person or a machine. For Voyager 1, this transition occurred billions of kilometers away from the warm light of the Sun, in a region where the very definition of space begins to change. We often think of the solar system as a collection of planets orbiting a central star, but to a physicist, the solar system is defined by the reach of the Sun's breath, and this breath, known as the solar wind, creates a vast protective bubble called the heliosphere. This bubble is our cosmic sanctuary, shielding the planets from the high-energy debris of the galaxy. For 35 years, Voyager 1 traveled within this familiar embrace, but in the summer of 2012, it reached the invisible wall where the Sun's influence finally gives way to the vast, cold sea of the Milky Way. Crossing this border, known as the heliopause, was not a sudden event like a ship hitting a coastline, but a complex, turbulent journey through the final outskirts of our star's kingdom. The journey toward this invisible border began long before the actual crossing. As the spacecraft moved further into the outer reaches, it first encountered the termination shock. Imagine a stream of water hitting a flat sink. It flows out smoothly and quickly until it hits a circular rim where it suddenly slows down and becomes turbulent. The termination shock is that rim for our solar system. Beyond it lies the heliosheath, a place where the solar wind is compressed and twisted by the pressure of the interstellar gas pushing back from the outside. Voyager 1 entered this transition zone in December of 2004. For the next 8 years, the spacecraft waded through this thick, stagnant plasma, its sensors searching for the definitive sign that it had left the Sun behind. It was a period of intense anticipation for the men and women at the Jet Propulsion Laboratory in California, many of whom had spent their entire careers following this single, lonely dot of light. The challenge of identifying the border was made infinitely more difficult by a stroke of bad luck that occurred decades earlier. In 1980, shortly after the spacecraft passed Saturn, its plasma science instrument, the very tool designed to measure the speed, density, and temperature of the solar wind, suffered a terminal failure. For 32 years, Voyager 1 was effectively flying blind to the most direct evidence of its surroundings. To determine if the craft had reached interstellar space, scientists had to rely on indirect clues. They looked at the intensity of charged particles and the direction of the magnetic field. Within the heliosphere, the spacecraft was surrounded by domestic particles, low-energy ions that had been blown out by the Sun. Outside, in the galaxy, it would be bombarded by foreign particles, high-energy cosmic rays originating from distant supernova explosions and the hearts of other stars. Throughout the early months of 2012, the data began to behave in ways that suggested the end was near. The domestic solar particles began to fluctuate wildly, dropping in intensity before surging back. It was as if the spacecraft were passing through a series of puddles or holes at the very edge of the sun's bubble. Then, on August 25, 2012, the domestic particles vanished almost entirely. Within a matter of days, the count of solar ions dropped by a factor of 1,000, while the flood of galactic cosmic rays jumped to its highest level ever recorded. To many, this was the eureka moment. Voyager 1 had seemingly broken through. However, your science is rarely so simple. A significant group of researchers remained skeptical because one crucial measurement did not match their models: the magnetic field. They expected that upon entering interstellar space, the direction of the magnetic field would shift dramatically as the craft moved from the sun's magnetic influence to that of the galaxy. But the field stayed stubbornly aligned in roughly the same direction. This discrepancy led to a year of intense debate within the scientific community. Some argued that Voyager 1 was in a magnetic highway, a final, strange region of the heliosphere where the sun's magnetic field lines were connected to the interstellar field, allowing particles to flow in and out while the craft was still technically inside. The National Aeronautics and Space Administration was cautious, refusing to officially declare that the craft had left the solar system. The mission was in a state of limbo, caught between two worlds. It took a violent event on the sun itself to provide the final proof. In the spring of 2013, a massive solar flare erupted, sending a wave of pressure through the solar system like a ripple in a pond. When this wave finally reached Voyager 1 a year later, it caused the thin gas around the spacecraft to vibrate. These vibrations, or plasma oscillations, were the key. By measuring the frequency of these sounds, scientists could calculate the density of the gas the spacecraft was currently traveling through. Cold interstellar gas is much denser than the hot, thin wind of the sun. The results were undeniable, and the gas surrounding Voyager 1 was 40 times denser than anything it had encountered inside the heliosphere. The spacecraft was not just near the border, it was well and truly outside. It was immersed in the interstellar medium, the raw material of the galaxy. With this data, the team was able to look back at the particle drops from August of 2012 and realize that was indeed the moment of departure. Voyager 1 had become the first human emissary to the stars, a feat that transformed it from a planetary explorer into a cosmic pioneer. What is this interstellar space that Voyager 1 now calls home? Many imagine it as a perfect vacuum, a total nothingness, but that is far from the truth. The space between the stars is filled with the ghosts of ancient celestial events. It is a thin soup of hydrogen and helium atoms, seasoned with the dust of stars that died billions of years ago. It is the womb of the galaxy, where new stars and planets will eventually be born from the slow collapse of these vast, tenuous clouds. For Voyager 1, this environment is remarkably stable compared to the turbulent heliosheath. The magnetic field is steady, the cosmic rays are constant, and the temperature is a frigid 3 degrees above absolute zero. In this quiet realm, the spacecraft is no longer buffeted by the sun's temperamental solar flares. It is sailing on the calm, deep waters of the Milky Way. The crossing of the heliopause changed our understanding of the sun's place in the galaxy. We discovered that the heliosphere is not a long, comet-like tail, as many had modeled, but perhaps something more symmetrical, shaped by the magnetic forces of the interstellar medium. We learned that the transition between our star's domain and the rest of the galaxy is a complex place of interaction, where the sun's breath piles up against the incoming galactic tide. Voyager 1's journey across this border showed us that the boundary is porous, a filter rather than a wall. It allowed us to measure the true nature of cosmic radiation without the distortion of the sun's magnetic shield, providing vital data for future generations of humans who might one day follow in the spacecraft's wake. As the spacecraft continues its journey further into this new territory, it is moving away from the sun at a speed of about 17 kilometers per second. Each year, it covers another 500 million kilometers of interstellar ground. To the scientists on Earth, the signals from the craft are getting weaker and weaker. The distance is so great that a command sent from a massive radio dish in Australia takes over 22 hours to reach the spacecraft, and the reply takes another 22 hours to return. This 44-hour round trip means that any interaction with the craft must be planned days in advance. The communication is a fragile thread, held together by the deep space network's most powerful antennas, which must listen for a signal that is 1 billion times weaker than the power used by a common electronic wristwatch. There is a certain poetry in the fact that Voyager 1 is now a creature of the stars. It was born on a planet that orbits a middle-aged yellow star, and it has now left that star's nursery. It is traveling through regions of space that have not been touched by solar wind for billions of years. In this sense, the invisible border was more than just a physical measurement. It was a transition in the craft's identity. Inside the heliosphere, it was a visitor. Outside, it is a permanent resident of the galaxy. It has entered a realm where the sun is just another point of light, no longer a majestic disk that dominates the sky, but a bright, distant lantern fading into the background of 100 billion other suns. The data gathered during and after this crossing remains some of the most precious information in the history of astronomy. Because Voyager 2 followed a different path and crossed the heliopause years later at a different location, we now have two separate points of data to help map the shape of our solar bubble. We have found that the border is dynamic, breathing in and out in response to the sun's 11-year activity cycle. When the sun is active, the bubble expands. When it is quiet, the bubble shrinks. Voyager 1 happened to cross during a period when the bubble was relatively stable, allowing for a clear transition. If it had arrived at a different time, it might have crossed the border multiple times as the heliopause shifted back and forth over the craft. As we look toward the future of Voyager 1's journey, we must recognize that while it has left the plasma solar system, it has not yet left the gravitational solar system. This is a common point of confusion. The interstellar medium begins at the heliopause, but the sun's gravity reaches much further. Thousands of small, icy bodies still orbit the sun far beyond the reach of its wind. Voyager 1 will spend many human lifetimes traveling through these distant, dark outposts before it can truly say it has left the sun's influence behind. But the crossing of 2012 remains the most significant milestone since the launch. It was the moment we stepped off the porch of our solar home and into the street of the galaxy. The silence of interstellar space is not empty. It is filled with the history of the universe. By measuring the composition of the gas and the energy of the cosmic rays, Voyager 1 is giving us a weather report from the deep galaxy. It is telling us about the environment that our entire solar system is moving through as it orbits the galactic center every 230 million years. We have discovered that we are currently moving through a relatively warm, thin cloud of gas known as the local interstellar cloud. Voyager 1's instruments are showing us the very leading edge of this encounter, providing a glimpse into the forces that shape the long-term environment of our planet. The crossing of the invisible border was a triumph of human persistence. It required a machine to function perfectly for over 3 decades in the most hostile environment imaginable. It required teams of scientists to pass their knowledge from one generation to the next, maintaining the ancient code and the aging hardware of the ground stations. When the announcement was finally made that Voyager 1 had reached interstellar space, it was more than just a scientific update. It was a moment of collective pride. We had sent a piece of ourselves into the great unknown, and it had survived the crossing. The small probe that had once looked at the rings of Saturn was now feeling the pulse of the galaxy itself. As Voyager 1 moves deeper into the cold mystery of the interstellar medium, it carries with it the hopes of a species that has always been defined by its need to see what is over the next horizon. The border it crossed in 2012 was the furthest any human-made object has ever gone, but in the context of the craft's total potential journey, it was just the first few steps outside the door. The vastness of the galaxy is so great that even at its incredible speed, Voyager 1 is still effectively standing still on a galactic scale. Yet, the fact that it is out there at all changes everything. We are no longer a species confined to a single bubble of solar gas. We are, through our mechanical representative, a part of the interstellar community. The crossing is complete. The shore has been left behind, and the vast, dark ocean now stretches out in every direction, waiting for the traveler to pass through its silent depths. Inside the skeletal frame of Voyager 1, there is no sound, no breath, and no warmth except for that which is generated by a tiny, fading heart of glowing metal. While the spacecraft has successfully crossed into the interstellar medium, its ability to remain a living entity, a machine capable of speaking back to its creators, is dictated by a ruthless and irreversible clock. To understand how far this traveler can go, we must look into the core of its engineering and the slow, the cold surrender of its power source. Voyager 1 is not powered by the sun. At its current distance of over 24 billion kilometers, the sun is merely a bright point in the heavens, providing no more energy than a distant porch light. Instead, the spacecraft relies on the heat of radioactive decay, a technology that was cutting edge in the 1970s and has since become an incredible testament to long-term survival. The power source consists of 3 radioisotope thermoelectric generators, often described as the nuclear batteries of the mission. These are 3 black cylinders mounted on a boom, far away from the delicate electronics to prevent radiation interference. Inside these cylinders are pellets of plutonium-238 dioxide. As the plutonium atoms naturally break apart through radioactive decay, they release a steady flow of heat. This heat is then converted into electricity through a process involving thermocouples, devices made of 2 different metals that produce a current when there is a temperature difference between them. When Voyager 1 left Earth, these generators produced about 470 watts of power, roughly enough to run a few household light bulbs. But the physics of the universe is a persistent thief. The plutonium has a natural decay rate, losing about half of its potency every 88 years, and the bimetallic thermocouples themselves degrade over time as they are baked in the heat of their own artificial star. Today, the power output of Voyager 1 has dropped to nearly half of what it was at launch. Every year, the spacecraft loses about 4 additional watts of power. This slow decline has forced the mission controllers on Earth into a state of permanent triage, a decades-long effort to balance the survival of the machine with the need for scientific data. It is a heartbreaking process of elimination. To keep the primary systems and the radio transmitter functioning, the team has had to systematically turn off the limbs and senses of the craft. The first to go were the cameras, which were deactivated in 1990 after taking the final portraits of the solar system. There was simply no more light to see, and the energy required to run the imaging heaters and processors was too precious to waste on empty darkness. Since then, the triage has moved into more critical territory. One by one, the heaters that keep the scientific instruments from freezing have been switched off. The ultraviolet spectrometer, the photopolarimeter, and various other sensors have been silenced. In recent years, the team has had to make even more difficult choices, turning off heaters for the remaining instruments that measure the magnetic field and the plasma environment of interstellar space. Remarkably, some of these instruments have continued to function far below their designed operating temperatures, showing a resilience that none of their original designers could have predicted. The spacecraft has become a cold machine, drifting through a void that is only a few degrees above absolute zero. Yet its ancient transistors continue to pulse with the dim remnants of its nuclear fire. The management of this dying heart is handled by a small, dedicated team at the Jet Propulsion Laboratory, some of whom were children or not even born when the craft was launched. They are the digital archaeologists of the modern era, working with computer code that was written in a language that is now almost forgotten. The memory of Voyager 1 is incredibly small by modern standards, only about 68 kilobytes. To put that in perspective, a single digital photograph taken today would be hundreds of times larger than the entire memory bank of the most distant human object. This limited memory is stored on ancient magnetic tape recorders and processed by 3 redundant computer systems. Because there is no room for error, every command sent to the craft is a masterpiece of efficiency, designed to squeeze every possible bit of utility out of a machine that is functionally a relic of the mid-20th century. One of the most remarkable examples of this intergenerational maintenance occurred in late 2023 and early 2024. The spacecraft began sending back a garbled, repetitive pattern of ones and zeros, a digital stutter that indicated a failure in the flight data subsystem. For months, it seemed that the mission might finally be over, as the brain of Voyager 1 was no longer able to package scientific or engineering data into a readable format. The team on Earth had to diagnose the problem from 24 billion kilometers away, knowing that every signal they sent took nearly a full day to reach the craft, and every response took another day to return. They eventually discovered that a single chip, responsible for storing a portion of the computer's software code, had failed. In an incredible feat of remote repair, the engineers wrote a new piece of code, broke it into sections, and hid it in different, healthy parts of the spacecraft's tiny memory bank. They had to ensure that these new instructions didn't interfere with other vital functions, like pointing the antenna or managing the power. When the command was finally executed and the first coherent data packet arrived back at the Deep Space Network after months of silence, it was a moment of triumph that echoed the original launch. It proved that as long as there is a spark of power in that plutonium heart, the human spirit can find a way to keep the conversation going. However, the The reality of the power curve is inescapable. By the middle of the 2020s, it is likely that the power will drop below the threshold required to run even a single scientific instrument. At that point, Voyager 1 will stop being a laboratory and become a simple beacon, sending back only basic pings of engineering data to tell us it is still there. Eventually, perhaps by 2030 or 2035, even the radio transmitter will fall silent. The last bit of energy will be used to maintain the internal clock or the basic emergency protocols, until finally, the thermocouples will stop producing enough current to trigger a signal. The heart will stop beating, and the spacecraft will go dark. But a dark spacecraft is not a dead spacecraft. One of the most common misconceptions is that the end of power means the end of the journey. In the vacuum of interstellar space, there is no air to cause friction and no rust to corrode metal. Once Voyager 1 goes silent, it will continue to travel at its current speed of 17 kilometers per second, propelled by the momentum it gained from Jupiter and Saturn decades ago. Without power, it will lose its ability to station keep. It will no longer be able to fire its tiny thrusters to keep its high-gain antenna pointed at Earth. It will begin to tumble, slowly and gracefully, as it drifts through the dark. The dying heart will be cold, but the body of the machine will remain almost perfectly preserved for hundreds of thousands, perhaps millions of years. The engineering of the thrusters is another marvel of the craft's endurance. For 47 years, Voyager 1 has used small bursts of hydrazine gas to maintain its orientation. In 2017, the primary thrusters had degraded to the point where they were no longer efficient. The mission team decided to attempt something that had not been done in 37 years. They fired up a set of trajectory correction maneuver thrusters that had been dormant since the encounter with Saturn in 1980. To their amazement, the thrusters worked perfectly. This ability to switch to backup systems that have been frozen for nearly 4 decades is a hallmark of the Voyager design philosophy. It was built for a marathon, not a sprint, with every component designed to withstand the unpredictable stresses of the deep void. As the power fades, we are also losing the last of the people who truly understand the machine. Many of the original engineers have passed away, and their knowledge has had to be meticulously documented and handed down to the next generation. The documentation itself is often on physical paper, stored in filing cabinets, containing hand-drawn diagrams of circuits that were soldered together by hand. Working on Voyager is a labor of love, a connection to a different era of exploration where the goal was not profit or immediate results, but the expansion of the human frontier. The dying heart of the spacecraft is mirrored by the aging of its creators, creating a poignant link between the flesh and blood world of Earth and the cold, aluminium world of the probe. What will be the last thing Voyager 1 says to us? It will likely be a simple engineering status report, a string of data points showing the temperature of the bus and the voltage of the remaining battery. There will be no final goodbye message, no poetic closing statement. There will simply be a signal that is too weak to be distinguished from the background noise of the universe. The great ear of the deep space network will listen, and where there was once a steady, rhythmic pulse of data, there will eventually be only the hiss of the stars. It will be a quiet end to the longest-running conversation in history. Even in its final, low-power state, the spacecraft continues to teach us about the durability of human intent. We sent a machine into an environment that should have destroyed it within years, and it has lasted for nearly half a century. It has survived the intense magnetic fields of Jupiter, the freezing shadows of Saturn's rings, and the constant scouring of the solar wind. It is now surviving the true cold of the galaxy. The fact that it is still functioning at all, given the primitive nature of its components, suggests that we may have vastly underestimated the lifespan of our technology when placed in the preservative environment of deep space. The dying heart of Voyager 1 is a metaphor for the human condition. We are finite beings, powered by a limited source of energy, trying to reach out and touch the infinite. The spacecraft's plutonium heart is a part of the Earth, a heavy element forged in the hearts of ancient stars and refined by human hands, and it is now returning to the stars. As the heat dissipates and the electricity ceases to flow, Voyager 1 will transition from an active explorer to a passive monument. It will become a message in a bottle that no longer needs to speak, for its very existence in the interstellar void will be a statement of what our species was capable of achieving during its brief time in the light. The silence that follows the final power loss will be absolute, but it will not be empty. The spacecraft will still carry the golden record, the copper disc plated in gold that contains the sounds and images of Earth. Even without electricity, the record remains a physical archive of our existence. If an alien civilization were to find the craft 1 billion years from now, they would not need the plutonium heart to be beating. They would only need to understand the physics of the groove and the needle. In this way, Voyager 1's journey is partitioned into 2 lives. The first, a life of power and speech that is now drawing to a close, and the second, a life of silence and endurance that will last as long as the galaxy itself. As we count down the remaining watts, there is a sense of gratitude rather than mourning. Voyager 1 was never supposed to last this long. Its primary mission was only supposed to last 4 years. Everything we have received since 1981 has been a bonus, a gift from a machine that refused to quit. The Dable heart has sustained a journey across billions of kilometers and decades of time, allowing us to see the edge of our world and the beginning of the next. When the final silence comes, it will be the silence of a job well done, of a traveler who has earned its rest. Voyager 1 will continue to sail, a dark, silent silhouette against the backdrop of the Milky Way, carrying the memory of the sun into the eternal night. When the final pulse of electricity flickers out and the radio transmitter falls into an eternal slumber, Voyager 1 will not disappear. In the vacuum of the deep, the concept of a finished mission is merely a human construct. To the universe, the spacecraft is just beginning its most endurance-testing phase. We now enter a period of the journey where the timescales shift from decades to millennia, and the landscape changes from the familiar celestial bodies of our neighborhood to a vast, ghostly frontier that few humans truly appreciate. This is the Oort Cloud, a theoretical yet mathematically certain shell of icy debris that represents the true gravitational edge of our solar system. It is a realm of frozen ghosts, ancient remnants of the dawn of time, and it is here that Voyager 1 will spend the vast majority of its next 30,000 years. To understand the scale of this journey, we must reconsider our mental map of the solar system. Most schoolroom diagrams show the planets crowded together, ending perhaps at Pluto or the Kuiper Belt. But the Sun's gravitational kingdom is far more expansive than the orbits of the 8 major planets. Beyond the heliopause, where the solar wind died away, there is a massive gap of empty space that Voyager 1 is currently traversing. It is moving at 17 kilometers per second, a speed that would carry a traveler from London to New York in just over 5 minutes. Yet, even at this blistering velocity, it will take approximately 300 years just to reach the inner edge of the Oort Cloud. For 3 centuries, the silent, dark probe will sail through an absolute void, a precursor to the most sparsely populated region of our star's domain. The Oort Cloud is named after the Dutch astronomer Jan Oort, who proposed its existence in 1950 to explain the origin of long-period comets. He reasoned that there must be a vast reservoir of icy bodies far beyond the planets, occasionally nudged toward the Sun by the gravity of passing stars. This cloud is not a flat disk like the asteroid belt. It is a giant, spherical bubble that surrounds the Sun in every direction. It begins at a distance of roughly 2,000 astronomical units, 1 astronomical unit being the distance between the Earth and the Sun, and extends perhaps as far as 100,000 or even 200,000 units into the dark. In kilometers, this is a distance so large that it is more easily measured in light years. The outer edge of the Oort Cloud may reach halfway to the nearest star. When Voyager 1 finally enters this frozen realm 300 years from now, it will find itself among the ghosts of the early solar system. These are trillions of objects ranging from the size of a mountain to the size of a small city, composed of water ice, ammonia, and methane. They are the leftovers from the formation of the planets 4.5 billion years ago. While the inner planets were baked by the Sun and the outer giants were swept into massive spheres of gas, these small bodies were flung into the deep freeze by the gravitational bullying of Jupiter and Saturn. They have remained there, unchanged and ossified, for the entire history of life on Earth. Voyager 1, when a relic of the 20th century, will drift among relics of the primordial nebula, a meeting of 2 different eras of solar history in the silent dark. It is important to dispel the Hollywood image of such regions. Voyager 1 will not be weaving through a dense thicket of ice boulders. The Oort Cloud is so vast that the distance between any 2 icy objects is likely hundreds of millions of kilometers. The spacecraft could spend its entire 30,000-year transit without ever seeing a single one of these ghosts up close. It is a journey through a profound and lonely emptiness where the Sun has shrunk to a particularly bright star, no longer providing warmth or a discernible disk, but still exerting a persistent, invisible tug. This is the paradox of Voyager 1's current state. It is moving fast enough to escape the Sun, and yet it is still technically a prisoner of solar gravity for the duration of this transit. The physics of this movement is a slow-motion escape. Because the spacecraft is no longer being accelerated by any engine or planetary assist, it is slowly losing a tiny fraction of its speed as it climbs out of the Sun's gravitational well. It is like a ball rolled up an incredibly long, shallow hill. However, the engineers at the Jet Propulsion Laboratory calculated the trajectory so perfectly that the Sun will never be able to pull it back. Voyager 1 has achieved escape velocity for the entire solar system. It is destined to leave, but the departure is a lingering, multi-millennial goodbye. As it sails through the Oort Cloud, the stars above will begin to shift their positions ever so slightly, a celestial navigation that the craft can no longer track, but which marks the passage of ages on its cold hull. What will happen to the machine during these 30,000 years of icy transit? In the absence of an atmosphere, There is no erosion in the traditional sense. There is no wind to scour the metal and no moisture to cause oxidation. However, space is not perfectly empty. The craft will be subject to a constant microscopic sandblasting by interstellar dust and micrometeoroids. These tiny particles, often no larger than a grain of smoke, strike the aluminium surfaces at tens of thousands of kilometers per hour. Over thousands of years, the smooth surfaces of the high-gain antenna and the scientific booms will become pitted and matte, etched by the relentless grit of the cosmos. The gold plating on the record cover may dull, and the delicate instruments may be slowly chipped away, but the structural integrity of the craft will likely remain intact. It is a sturdy vessel, built to withstand the rigors of Jupiter, and the Oort Cloud, for all its vastness, is a relatively quiet neighborhood. The passage through the Oort Cloud represents a significant gap in our own human perspective. 30,000 years into the future is a span of time that is difficult for us to comprehend. 30,000 years ago, humans were painting images of bison and mammoths on the walls of caves in what is now France and Spain. We were using stone tools and had not yet conceived of agriculture, writing, or the wheel. If we look forward an equivalent amount of time, there is no way to predict what will have become of our species. We may have spread to other stars, or we may have returned to the dust from which we came. Regardless of our fate, Voyager 1 will continue its silent trek through the Oort Cloud, a mechanical emissary from a time when we first dared to look up and wonder how far we could go. This section of the voyage is where the spacecraft truly becomes a ghost itself. Without power, it is a dark, non-reflective object, almost impossible to detect even if someone were looking for it. It carries the sounds of humpback whales, the laughter of children, and the music of Bach into a region where the temperature is barely above absolute zero. There is a haunting beauty to this image, a silent archive of human joy and sorrow, drifting through a graveyard of ice that predates our existence. It is the ultimate time capsule, protected by the very emptiness that makes its journey so difficult. The Oort Cloud acts as a buffer, a vast transition zone where the solar system ends and the true galaxy begins. By the time Voyager 1 reaches the outer limits of the Oort Cloud, roughly 32,000 years from now, it will finally be free of the Sun's gravitational influence. At this point, the gravity of other stars in the Milky Way will begin to have a greater effect on its path than the star that birthed it. It will have officially graduated from being a solar object to a galactic one. The Sun will have faded into the background of the constellations, just one of many billions of lights in the spiral arms of the galaxy. The invisible border of the heliopause was a chemical and magnetic exit, but the exit from the Oort Cloud is the final gravitational divorce. During this long transit, Voyager 1 will also be a witness to the breathing of the solar system. The Oort Cloud is not static. As the Sun moves through the galaxy, it occasionally passes near other stars. These stellar flybys can compress the Oort Cloud, sending showers of comets inward toward the planets. Voyager 1 will be out there in the thick of it, a silent observer to the gravitational tides that have occasionally caused mass extinctions on its home planet. It is sailing through the very machinery of cosmic catastrophe and creation, the place where the seeds of water and organic molecules were stored before being delivered to the inner planets billions of years ago. The engineering that allows for this 30,000-year survival is perhaps the most human aspect of the story. The designers used materials like titanium and high-grade aluminium, and they shielded the electronics in a vault to protect them from radiation. While they were thinking about the 5-year mission to Saturn, they unintentionally created a monument that could last for an epoch. The gold-plated record, in particular, was designed with a lifespan of over 1,000 million years. Even if the spacecraft is eventually reduced to a battered skeleton by the dust of the Oort Cloud, the record, bolted to the side of the bus, is likely to survive in a readable state. It is the heart of the ghost, a golden soul that carries the frequency of our world. As we contemplate Voyager 1 sailing through the frozen realm, we must also consider the silence of the journey. In the Oort Cloud, there is no radio interference, no solar noise, and no planetary magnetic fields. It is a silence so profound that it would be terrifying to a human mind. But for the spacecraft, it is the natural state of things. The vibrations of its launch and the hum of its active years are now a distant, ancient memory. It has become part of the background of the universe, a small, cold rock with a complex interior, moving according to the dictates of Newton and Einstein. It is the ultimate expression of inertia, a body in motion that will stay in motion until acted upon by an external force. And in the Oort Cloud, such forces are few and far between. The transition from the inner Oort Cloud to the outer reaches is marked by a thinning of the icy population. The ghosts become even more spectral, their orbits stretched so thin by the influence of passing stars that they are barely clinging to the sun. Here at the very precipice of the interstellar deep, Voyager 1 will experience its final moments as a member of the solar family. It is a 30,000-year walk to the edge of the driveway. Once it crosses the outer boundary, the spacecraft will be in the true wilderness of the galaxy, the space between the stars, where no single sun dominates and where the path is guided by the collective mass of the Milky Way's 100 billion stars. This journey through the icy realm is a reminder of our own fragility. We live in the warm, bright center of a bubble that is surrounded by a vast, cold and dark wilderness. Voyager 1 is the only part of us that has seen the fence, and it is the only part of us that will ever cross it in our current form. The Oort Cloud is the final barrier, the ultimate frontier of our home. By crossing it, Voyager 1 proves that human ambition is not limited by the lifespan of our bodies or the stability of our civilizations. We can build things that outlast our history. We can cast our thoughts into the frozen realm and know that they will endure, sailing through the ghosts of the past toward an unknown and distant future. When the spacecraft finally emerges from the outer Oort Cloud, it will be a different kind of entity. It will be an interstellar wanderer, free of its parent star, embarking on a voyage that could last for millions of years. But the 30,000 years it spent among the ice will have been its most defining period of endurance. It will have survived the long, dark winter of the solar system's edge, proving that even a small machine from a small planet can navigate the frozen realm of ghosts and emerge on the other side, still carrying the message of a species that wanted to be remembered among the stars. The Oort Cloud is not the end. It is the long, quiet hallway that leads to the rest of the universe. Beyond the outer fringes of the Oort Cloud, the tether that once bound Voyager 1 to the Sun is finally severed. For 30,000 years, the spacecraft was a creature of our star's gravity, a lingering guest in a vast hallway of ice. But eventually, the pull of the distant collective mass of the Milky Way becomes stronger than the tug of the fading sun. At this moment, Voyager 1 truly begins its career as a galactic wanderer. It is no longer an Earth-launched probe returning a report to its masters. It is an independent satellite of the galaxy itself, orbiting the massive central black hole of the Milky Way on a journey that will last for millions and potentially billions of years. To contemplate how far the craft can travel in this era is to step away from the history of humans and into the history of the universe itself. The first major milestone in this eternal drift occurs approximately 40,000 years into the future. By this time, the constellations that we recognize today, Orion, the Great Bear, and the Southern Cross, will have warped and dissolved, their stars having moved into new positions relative to one another. Voyager 1 will be passing through the constellation of Camelopardalis, the giraffe. It is not headed toward a specific star to find a new home. It is simply passing through the neighborhood. Its closest approach will be to a star currently known as Gliese 445. This is a dim, red dwarf star, far smaller and cooler than our Sun. Even at its closest point, Voyager 1 will still be 1.6 light-years away from the star, a distance of over 15 trillion kilometers. To any hypothetical inhabitants of a planet orbiting Gliese 445, the spacecraft would be entirely invisible, a cold, dark needle in a haystack of infinite proportions. This encounter highlights the fundamental reality of interstellar travel. The universe is mostly empty space. Even when we say a spacecraft reaches another star, it is often passing by at a distance that makes the word encounter seem like an exaggeration. Yet, this is the destiny of Voyager 1 for the next several million years. It will continue to drift through the spiral arms of the galaxy, occasionally passing through the outskirts of other stellar systems. It will sail past red dwarfs, white dwarfs, and perhaps the massive blue giants that burn hot and die young. Each of these stars will exert a tiny gravitational nudge on the craft, subtly altering its course. Over hundreds of thousands of years, these small changes will add up, carving a winding, serpentine path through the stellar sea. As Voyager 1 travels, it will be moving through the weather of the galaxy. While the interstellar medium is a near vacuum, it is not uniform. The spacecraft will pass through vast clouds of cold gas and dust, known as molecular clouds. These are the nurseries where gravity pulls matter together to form new generations of stars. For thousands of years at a time, the probe might be immersed in a thin, glowing fog of hydrogen, the light of distant stars filtered and reddened by the surrounding dust. In these regions, the sandblasting effect mentioned earlier will intensify. The spacecraft, moving at 17 kilometers per second, will collide with millions of atoms and dust grains every hour. While each impact is insignificant, the cumulative effect over millions of years will continue to wear down the machine. The high-gain antenna, once a pristine white dish, may eventually be eroded away entirely, leaving only the sturdier titanium frame and the most dense internal components. Despite this slow erosion, the spacecraft is incredibly persistent. In the environment of the deep galaxy, there is no heat to melt it, no oxygen to burn it, and no liquid to dissolve it. It is protected by the very cold and the very vacuum that make it so inhospitable to life. It is possible that the body of Voyager 1, the central bus and the structural beams, could remain recognizable for hundreds of millions of years. It will become a part of the galactic archaeology, a piece of technological fossils drifting among the natural debris of the Milky Way. If we were to look at the galaxy from above, We would see Voyager 1 following a massive circular path around the galactic center, a journey that takes roughly 225 to 250 million years to complete one single galactic year. This timescale is where the journey becomes truly staggering. One full orbit of the galaxy would bring Voyager 1 back toward the region of space where it began, but the Sun and the Earth will have moved on. In the time it takes for the craft to complete one galactic year, the Earth itself will have undergone massive changes. Tectonic plates will have shifted to form new supercontinents, and the evolution of life will have moved into entirely new and unpredictable directions. By the time Voyager 1 finishes its second or third orbit, the Sun will be beginning its slow transition toward the end of its life. Over the next 5 billion years, as the craft continues its silent circles, our star will swell into a red giant, consuming Mercury, Venus, and perhaps the Earth itself. The cradle that built the traveler will be destroyed, but the traveler will still be out there, sailing through the darkness, carrying the memory of the world that was once its home. There is a profound irony in the fact that Voyager 1 may outlast the Sun. It was created using the materials of the Earth, elements that were themselves forged in the explosions of even older stars. By returning to the interstellar medium, the spacecraft is completing a cycle of matter that began billions of years ago. It is a piece of the solar system being returned to the galaxy. As it drifts, it will witness the slow metabolism of the Milky Way. It will see stars die in brilliant supernova explosions, seeding the surrounding space with heavy elements. And it will see those elements coalesce into new stars and planets. Voyager 1 will be a silent, unmoving witness to the grandest cycles of the cosmos, a tiny, artificial grain of sand in a desert of 100 billion suns. What will the spacecraft look like after a billion years of travel? It will be a battered, pitted skeleton of its former self. The long booms that held the magnetometers and the nuclear batteries may have snapped off due to the stress of repeated micro-impacts or the subtle internal stresses of the metal over aeons. The gold-plated record, however, is shielded by a thick aluminum cover and bolted to the side of the main body. Even if the rest of the craft is unrecognizable, the record and its cover are likely to survive. They are made of materials designed to endure for 1,000 million years. In the etched instructions on how to play the record, the map of the pulsars showing the location of our Sun, and the images of our species will remain as a permanent physical record of a moment in time when a small civilization decided to speak to the future. The path of Voyager 1 is not just a line, it is a story of cosmic isolation. As the millions of years pass, the spacecraft will move between the spiral arms of the galaxy, entering the interarm regions where the stars are fewer and the darkness is even more absolute. It will experience periods of galactic winter, where it is far from any source of light or heat, followed by galactic summers as it passes through the dense, bright neighborhoods of the inner spiral. It is a wanderer with no destination, a ship with no shore. Yet, it is exactly this lack of a destination that ensures its longevity. Because it is not aimed at a star, it is unlikely to ever crash into one. The chances of it being captured by the gravity of a planet and being pulled into a destructive entry are nearly zero. It is much more likely that it will simply continue to orbit the galaxy until the galaxy itself changes. As we look even further into the future, tens of billions of years from now, the Milky Way will undergo a massive transformation. It is currently on a collision course with its neighbor, the Andromeda Galaxy. In about 4 or 5 billion years, these two massive structures will begin to merge in a spectacular celestial dance. The stars themselves will rarely collide, but the gravitational tides will be enormous. Whole solar systems will be flung into new orbits, and the gas clouds will be compressed to trigger a final, massive burst of star formation. Voyager 1 will be caught in this merger, its path through the stars becoming even more chaotic as the two galaxies become one. It will eventually find itself in a new, even larger elliptical galaxy, perhaps nicknamed Milkdromeda, continuing its silent drift in a brand new cosmic environment. The endurance of the spacecraft is a testament to the laws of motion. In our daily lives, everything eventually stops. Friction, air resistance, and gravity bring all things to a halt. But in the deep drift of the galaxy, there is almost nothing to stop a body in motion. Voyager 1 is a demonstration of the purity of physics. It is the ultimate expression of the long game. While we struggle to build buildings that last for 1,000 years or civilizations that last for a millennium, we have accidentally built a machine that could theoretically exist until the heat death of the universe, billions upon billions of years from now. It will be out there when the last stars begin to flicker and die, a relic of a time when the universe was young and full of light. The eternal drift also raises questions about the nature of our legacy. If a machine can travel this far and last this long, what does it mean for our definition of success? We often measure ourselves by our buildings, our art, and our wars, but all of those things are transient. They are subject to the erosion of time and the instability of our planet. And Voyager 1 is our only truly permanent achievement. It is the only thing we have ever made that is not subject to the Earth's expiration date. Even if no one ever finds it, the fact that it exists, that a specific arrangement of atoms was once put together by a group of primates on a blue planet, is a permanent change to the state of the universe. It is a scar on the void, a tiny, indelible mark that says, "We were here." As the spacecraft drifts among the distant alien suns, it also serves as a reminder of the scale of our ignorance. We have mapped the path of the probe for the next few million years, but there is so much we do not know about the galaxy it is traversing. We do not know how many planets it will pass, how many alien civilizations might be looking at the same stars from the other side, or what strange phenomena it might encounter in the deep voids between the arms. Voyager 1 is our scout, but it is a scout that can never report back. It is a one-way transmission into the deep future. It is the ultimate act of faith, sending a message without any expectation of a reply, purely for the sake of the message itself. The silence of this phase of the journey is different from the silence of the Oort Cloud. In the Oort Cloud, the craft was still a local object, a part of our star's family. In the eternal drift, it is a citizen of the Milky Way. The sun is no longer a special point of origin. It is just another yellow star in a sea of yellow stars. Voyager 1 has lost its context. To an outsider finding the craft in the distant future, its origin would be a mystery that could only be solved by decoding the pulsar map on the record's cover. It is a piece of art that has been stripped of its gallery, a book that has been lost from its library. Yet, the book is still readable and the art is still there. The far in How Far Can the Voyager 1 Travel is not just a distance in kilometers, it is a distance in time. It can travel far enough to see the end of the world, the birth of new galaxies, and the slow cooling of the cosmos, it can travel far enough to outlast the memory of every king, every empire, and every language that has ever existed on Earth. It is a traveler that has transcended its creators. We are the fleeting, flickering sparks of life that gave it the initial push, but it is the one that will see the long, one dark story of the universe through to its conclusion. In the end, the drift among the stars is a journey of pure existence. There is no more data to collect, no more power to manage, and no more borders to cross. There is only the steady, relentless movement through the dark. Voyager 1 will be a tiny, silent companion to the stars, moving in perfect harmony with the rotation of the galaxy. It will be a monument to the 1970s, to the engineers of the Jet Propulsion Laboratory, and to the species that wanted to reach out and touch the infinite. It is our shadow on the stars, a small, cold, but enduring piece of humanity that will never, ever come home. As it sails through the alien suns, it carries the quiet dignity of a messenger who has forgotten the message, but continues to run, simply because that is what it was built to do. The eternal drift is the final state of the craft. It is the transition from a tool to a relic, from a machine to a legend. Voyager 1 is the furthest we have ever gone, not just because of the kilometers it has covered, but because of the vast, echoing silence it has entered. It is the pioneer of the deep future, the first of us to truly leave the nursery and enter the great dark house of the galaxy. And as it moves through that house, it will be the most distant, the most lonely, and the most permanent thing we have ever achieved. The stars will watch it pass, a dark silhouette against the glowing clouds of the Milky Way, as it continues its voyage into the forever. As we gaze into the most distant reaches of the future, past the era of the gas giants, beyond the crossing of the heliopause, and through the tens of thousands of years spent navigating the Oort Cloud, we must finally confront the ultimate purpose of Voyager 1. When the last radioactive pellet has cooled and the metal has been etched into a dull gray shadow by the grit of the galaxy, the spacecraft ceases to be a machine of measurement and becomes a machine of memory. It is a silent messenger for the deepest future, a role it was prepared for before it ever left the assembly floor in Southern California. Bolted to the side of the central bus is a 12-inch gold-plated copper disc, a physical archive that represents the most ambitious attempt in history to summarize the human experience for an audience that may not even share our biological foundations. To ask how far Voyager 1 can travel is to ask how long the memory of our species can endure in a universe that is indifferent to our existence. The Golden Record was the brainchild of a small committee led by Carl Sagan, a group of visionaries who understood that Voyager 1 was not just a scientific mission, but a cultural one. They realized that because the spacecraft was destined to wander the vacuum of interstellar space for millions of years, it offered a unique opportunity to send a message into the deep time of the cosmos. The record is protected by an aluminum jacket, etched with symbols that serve as a universal language. There are no words on the cover, for the designers knew that human languages are transient and localized. Instead, they used the fundamental language of the universe, mathematics and physics. They etched a diagram of the hydrogen atom, the most abundant element in the cosmos, to serve as a fundamental clock and ruler. By using the transition of a hydrogen electron as a unit of time, any scientifically literate civilization would be able to understand how fast to spin the record and how to decode the images and sounds contained within the grooves. Inside those grooves is a portrait of a world that will likely be long gone by the time the record is ever found. There are 115 images encoded as analog signals, ranging from photographs of the Great Wall of China and the Taj Mahal to diagrams of the human DNA molecule and the structure of our solar system. There are images of people eating, drinking, and walking, of children playing, and of the diverse animals that share our planetary home. It is a carefully curated selection intended to show the best of what we were. It avoids the scars of our history, the wars, the poverty, and the environmental destruction, choosing instead to present humanity as a curious, creative, and hopeful species. It is a letter to the future that we would want to read ourselves, a reminder of the potential we held during our brief moment in the sun. The sounds of the record are perhaps even more evocative than the images. There are greetings in 55 different human languages, beginning with Akkadian, a language spoken in ancient Mesopotamia thousands of years ago, and ending with Wu, a modern Chinese dialect. There are the sounds of Earth, the roar of a thunderstorm, the rhythmic pulsing of a human heartbeat, the wind in the trees, and the haunting songs of humpback whales. There is the laughter of a child and the sound of a mother's kiss. And then there is the music. The selection spans the breadth of human creativity, from the intricate mathematical beauty of Johann Sebastian Bach to the raw, electric energy of Chuck Berry. There are folk songs from the mountains of Peru, wedding songs from the Balkans, and the meditative drones of the Japanese shakuhachi flute. It is a symphonic celebration of life, a vibration of air from a small planet, now transformed into a physical groove in a gold-plated disc and sent into a realm where there is no air to carry sound at all. The engineering of the record is as impressive as its content. Gold was chosen not for its value, but for its stability. Gold does not tarnish or corrode, and when plated over copper, it provides a surface that can remain readable for over 1,000 million years. This is the far in the journey of Voyager 1. 1 billion years is a span of time that defies human logic. In 1 billion years, the continental plates of Earth will have recycled themselves many times over. The oceans may have evaporated as the sun grows hotter. Life on our planet may have evolved into forms that would be unrecognizable to us, or it may have vanished entirely. Yet Voyager 1 will still be out there, and the record will still be attached to its side. Even if the spacecraft itself is battered and broken, the record is the most durable piece of our legacy, a golden thumbprint in the galactic record. The pulsar map on the cover is the most daring part of the message. When it uses 14 pulsars, rapidly spinning neutron stars that act as cosmic lighthouses, to triangulate the position of our sun. Because pulsars age and their spin rates slow down over millions of years, the map also serves as a timestamp. An advanced civilization finding the craft could look at the map, measure the current spin rates of those same pulsars, and calculate exactly when the spacecraft was launched and from where. We have given the universe our address and our time, a bold act of vulnerability for a species that has spent much of its history hiding from the predators of its own world. It is a statement of trust in the cosmos, a belief that anyone capable of finding a small probe in the vastness of the galaxy must also be a species that has moved beyond the need for primitive aggression. But as we reflect on this silent messenger, we must also consider the possibility that it will never be found. The galaxy is so vast, and the stars are so far apart, that the chances of a random encounter between a spacecraft and an alien civilization are almost zero. Voyager 1 is less than a grain of dust in a desert the size of a continent. It is entirely possible that for the next several billion years, the spacecraft will simply orbit the galactic center in total isolation, a dark and silent witness to the slow evolution of the Milky Way. In this scenario, the record is not a message to others, but a monument for ourselves. It is a way of saying that we were here, that we mattered, and that we tried to reach out. It is a physical embodiment of our refusal to be forgotten by the universe. But the ultimate fate of Voyager 1 is tied to the ultimate fate of the universe. In the extremely deep future, long after the Sun has died and the Milky Way has merged with Andromeda, the spacecraft will continue to exist in some form. If the universe continues to expand forever, as current theories suggest, the galaxy will eventually become a lonely island in a sea of darkness. The stars will burn out, leaving only the cold cinders of white dwarfs and the silent maws of black holes. Voyager 1 will be an artifact of the stelliferous era, the brief, bright period of the universe's history when stars still shone and life was still possible. It will be a relic of the era of light, drifting through the era of darkness. Even if it is eventually struck by a stray atom of interstellar dust that finally breaks its last structural bond, and the atoms that made up the craft will still be there, carrying the heavy elements forged on Earth into the infinite expansion. There is a profound comfort in the existence of Voyager 1. We live in a world of constant change and increasing fragility. Our digital records are easily erased, our buildings crumble, and our very history is subject to the whims of politics and time. But out there, beyond the reach of our human failures, is a piece of us that is nearly indestructible. Voyager 1 is our long-form art, a masterpiece that requires 1 billion years to truly appreciate. It is the only thing we have ever made that is truly commensurate with the scale of the universe itself. It reflects our capacity for precision, our appetite for discovery, and our deep-seated need to connect with something larger than ourselves. The journey of Voyager 1 is also a reminder of the power of intergenerational cooperation. The mission was launched by a generation that is now aging, and it is being maintained by a generation that was not yet born when it left. The record was designed by people who are now gone, yet their voices and their choices remain the primary representation of our species in the stars. This continuity of purpose is rare in human history. It suggests that when we set our sights on the stars, we are capable of thinking and acting across timescales that far exceed our own lifespans. Voyager 1 is a bridge between the present and the deep future, a connection between the fleeting and the eternal. As we conclude this exploration of how far the traveler can go, we realize that the answer is not a number. Voyager 1 can travel as far as the laws of physics allow, and as long as the material of its construction can resist the slow erosion of the vacuum. It can travel to the end of our Sun, to the merger of our galaxy, and perhaps to the end of time itself. But more importantly, it travels into the imagination of every person who looks up at the night sky and wonders what else is out there. It is a symbol of our curiosity, a machine that has transcended its mechanical parts to become a legend. It is the furthest we have ever reached, and it remains the standard by which all our future explorations will be measured. The story of Voyager 1 began with a rare alignment of the planets, a moment of celestial opportunity that we were wise enough to seize. It has been a journey of constant discovery, from the volcanic moons of Jupiter and the complex rings of Saturn to the mysterious magnetic border of the heliopause. It has been a story of survival, of a dying heart that refused to stop beating, and a team of engineers who refused to let go. And it is now a story of silence, of a dark and cold messenger sailing through the Oort Cloud and into the eternal drift of the galaxy. It is the longest, loneliest, and most beautiful voyage in the history of our world. When we think of Voyager 1 today, we should not think of it as a piece of old technology fading away. We should think of it as the leading edge of humanity. It is the only part of us that has seen the stars as they truly are, without the distortion of an atmosphere or the protective shield of a sun. It is our scout in the wilderness, our representative in the galactic assembly. It carries our music, our faces, and our heartbeat into the great dark ocean, and it does so with a quiet dignity that reflects the best of our nature. It is a silent messenger for the deepest future, and its journey is just beginning. In the final accounting of our species, Voyager 1 may be our most important work. Long after our cities have been reclaimed by the Earth and our names have been lost to the winds, this small, battered probe will still be moving through the stars. It will be the only evidence that a group of curious primates once lived on a small blue planet and looked up at the stars with enough wonder to send a piece of themselves to join them. It is the ultimate message in a bottle, cast into the cosmic sea by a civilization that wanted to say, simply and clearly, that we were here and we were part of the story. The far of Voyager 1 is infinite. It is a journey that has no end, a path that stretches out into the billion-year horizon. It is the furthest any human has ever gone, and it is the furthest any of our works will ever survive. As it sails through the silent night, we can take pride in knowing that we have reached out and touched the stars. The traveler is out there, moving at 17 kilometers per second, carrying the memory of the sun into the eternal dark. And in its silence, it speaks more loudly than any words we could ever say. It is the monument of our existence, a golden soul drifting through the stars forever.